Welcome to Brain Vision.
Hi everyone, so what we have is saturated R134a moving through a condensing tube at 0.1 kilograms per minute, and we're starting at a temperature of 34 degrees Celsius. What we're asked to find is the rate of heat transfer when the final temperature is 34 degrees C, and also when the final temperature is equal to 20 degrees C. So what we're going to go ahead and do is state our assumptions. Our assumptions is that we're at steady state conditions and that our kinetic and potential energies are negligible, and that there's no work interaction that's involved. Go ahead and write that as work equals 0. So now what we can do is go ahead and find the properties of our saturated refrigerant-134a at 34 degrees C. So we'll see that at 34 degrees C we have an HF equal to 99.41 kilojoules per kilogram. We have an HFG equal to 169.21 kilojoules per kilogram, and an HG equal to 268.61 kilojoules per kilogram. And we'll also do this for 20 degrees C. So at 20 degrees C, all we're really looking for is our HF. We know that HF will be equal to 79.32 kilojoules per kilogram. Now we're getting all these quantities from our thermodynamic tables. Next, what we're going to do is define our system. So we're actually going to go ahead and define the tube and the refrigerant as our system. And the control volume is going to be this, because we have mass that's passing through the boundaries. Again, we're assuming that steady state, so we know that the mass that's coming in is equal to the mass that's leaving. And now what we can do is go ahead and write our energy balance. So we can say that E dot in minus E dot out is equal to the change in energy of the system. Now remember, we said that this system is a steady state, so that means this total system energy itself is not changing. Therefore, we can write that the rate of energy incoming is the rate of energy leaving. Now we can go ahead and plug in for this and say that the incoming enthalpy is going to be equal to the rate of heat transfer plus the enthalpy leaving after condensation. So we can rewrite this and say that the rate of heat transfer is going to be equal to m dot h1 minus h2. And what we're going to assume is that H1, which is the inlet condition enthalpy, is actually going to be equal to Hg, since we are at a saturated state. So we can go ahead and say that H1 is equal to Hg at our starting position at T equal to 34 degrees Celsius. So now we can actually just go ahead and solve for this Q out. So for our first case at 34 degrees C as our outlet temperature, we can say that our H2, so our exit enthalpy, is going to be the HF at 34 degrees C, and this is equal to 99.41 kilojoules per kilogram. Now we can say that Q out is equal to m dot H1 minus H2. Now, as I said before, H1 is just Hg, so we can go ahead and solve for this Q out, which gives us a Q out of 16.9 kilojoules per minute. So this is our Q out when our exit temperature is 34 degrees C. Now we're also asked to solve for the heat transfer when our exit temperature is 20 degrees C. So when our exit temperature is 20 degrees C, our exit enthalpy is going to be our HF at 20 degrees C, which we looked up in the table, and that was 79.32 kilojoules per kilogram. We're going to go ahead and plug our equation in for Q out. So we have m dot H1 minus H2. And remember, our H1 is still the same as the 34 degree case. So after plugging that in, what we get is a Q out equal to 18.9 kilojoules per minute. Excuse me. And that is our final answer.